什么时候我们吃个饭讨论一下这个问题？下礼拜天我就回去了。也去地方。啊，他每次不来，他不太好。今天又6号，早上上12点，那得必须上课。
那是我差一点数学这一期了。
不至于。
没有，我这周的要求上没什么。今天不是今天是今天是2，是1月份有。给你猜一个，看一下我。Okay, I'm just gonna give the really need screen, but I was going to just show really quickly on the schedule page. So yeah, so the schedule page is, if you take a look, is filled out now all the way to the end of the semester. It's penciled in. The last day we have, again, so penciled in. We'll see how things pan out with when you turn in proposals, but we're hoping to do the final day of just quick 5-minute or so project presentations from everybody's groups. Yeah, everything is in here just to give you an idea of what we're doing. So we're in the middle of Lie groups and related topics today and next time. We'll finish that. After Lie groups, Lie algebras, we're going to do some unsupervised learning, self-supervised learning, and flow-based models. We'll see that those are diffeomorphic, manifold diffeomorphisms modeled through deep neural networks. So that I should mention, yeah, that after we do Lie groups is kind of pretty mathy. The Lie group actions is going to be a little bit more applied to modern kind of neural network stuff. And so these references are a couple of examples. I'll give maybe another couple more. I can dig up a couple more examples of Lie groups in neural networks. Okay, so 98 is not modern. I take it back. So this one's pseudo modern. There's more recent. I'll try to pull up a more recent reference of just an example. We'll quickly kind of skim the principles there to where Lie group stuff is being applied in machine learning. Yeah, and so then this section here, before we get to our election day break, day off, Amon's gonna be taking this stuff, and it's much more machine learning methodology, but you'll see the manifold geometry and concepts that we've been doing coming up there. And then just giving kind of a overview. We mentioned very early first week of class in the course overview that we would be talking about information theory and information geometry. This is where we have statistical models or machine learning models that have parameters, and those parameters that we're trying to learn when we say we're learning a model on data, we can put a manifold geometry on the actual parameters. So far in the past, we've been talking about manifold geometry of the data, but your parameters can also be thought of as living on manifolds. And that's kind of what information geometry talks about. And the natural gradients we'll see are part of that. And it ties into score-based generative models, which you may have heard of. And this includes things like diffusion models, which will kind of segue into that. Another topic, graph neural networks. This again will be Aman doing diffusion models and graph neural networks, where geometry comes into play there. We have another break and more information theory, probably, although this last couple of lectures, we might switch it up depending on how things go and if we stay on schedule and everything. So yes, that's basically what to look forward to at the kind of this last half or so of whatever we have left. Okay. Any questions about the schedule? Yeah.
Is the assignment tab uploaded on Canvas?
Not yet. Yeah. Oh, yeah. So the other thing, the schedule, homework 3, I'm going to post today as soon as I get back to my office and get it up there. I was trying to get it up before class, but homework 3 will be out today. I'll send an email just so everybody takes a look at it. But just as a preview, I don't have it to pull up here, but what you're going to be doing there is autoencoders. So if you watched the lecture from last week that Aman gave on variational autoencoders, you're going to be, I've already pre-trained some autoencoders. You're welcome to retrain them if you have like, a GPU that you want to retrain into the model. But to make it simple, I did all the training of the models just to make it, that's not, it's kind of boring. You can tinker with the models, play with them and retrain if you want. That's totally acceptable. But I pre-trained them so you don't have to do that if you don't want to. What you're going to be doing there is looking at the manifold, again, the concept of immersion and submersion we talked about, where we can think of layers of a neural network as mapping our manifold of data through smooth mappings or differentiable mappings, with the caveat if you have differentiable activation functions, and testing whether those mappings are immersion, so they preserve sort of this manifold, they immerse. If you think of generative models immersing, maybe I'll draw a picture. Let me just double check my Zoom camera is. No, it's here we go. Okay. So let me just draw a picture to kind of set the stage for when you take a look at the homework. Once I send the email this afternoon, I recommend taking a look at it as soon as you can. So the idea is that this autoencoder, I have a data manifold. This is my data. Somehow, what we would like to have be the case is that our data manifold is encoded into a latent space. And this is kind of like related to the manifold learning stuff that we did, but it's with root neural networks. You have a latent space, which is just the vector space. This is our D. There is the encoder. I was right at ENC, but you can give it a math notation if you want. Encoder that takes your original data, let's call it X's, into a latent space, which we'll call Z. Okay, and then you have a decoder in the autoencoder framework that takes this latent representation, decodes it into, I'll call it X tilde, or a reconstructed data point. It's trying to match the original data point that was encoded. And what you would like to have happen is that this is a lossless process, that you can encode perfectly, kind of saving all the information needed in the data to decode it back so that X tilde is equal to X. And the way we usually train these things, and I think I've got the code that I use to train the things. It's very, very, very simplistic, just basic autoencoder with a mean squared error loss. So you encode and decode, and your loss function is how close is X to X tilde. And that's what you optimize, you try to minimize. So yeah, that's what we would like to have happen is you can encode to a Z, decode to an X tilde, and you get the same thing back always. And that anything that's a valid point in your data manifold would map to some type of Z that would be able to faithfully restore or reconstruct that data. And we could do this if, and I should mention, right, this data is really on a lower dimensional manifold living in a higher dimensional, let's say R capital V, where capital V is much bigger than little d. And what you would like to have be the case is that the dimensionality of your data manifold, and again, it's questionable whether it actually lives on a manifold or not, but that's our model. Our data manifold would be, you would like it to be at least able to fit in little d. Your best case scenario, you have little d be the data manifold dimension and your latent space dimension would match, but you at least need enough dimensions here that you don't lose important dimensions that are along the manifold. If you squash dimensions, you've lost information. You would like to lose dimensions that are perpendicular to the manifold, or maybe if you have some noise removal is fine also, but that's the idea. And we had this concept of a submersion. You'd like kind of encoders, if best case scenario, submerge this manifold into your latent space, and an immersion is a little bit easier to satisfy, but you would like your decoder to be an immersion in the sense that this d-dimensional manifold is immersed so that any kind of set of dimensions that you'd have at least locally at a point would still be non-degenerate dimensions that you could move along as you go up to your data space. So any kind of movement along here doesn't become degenerate. Otherwise, you're wasting latent dimensions you don't need. If a latent dimension gets squashed, then it's not really doing anything. You could toss that dimension. And so the immersion property guarantees that you at least have an immersed manifold that you're representing up here, and that movement in your latent space is actually meaningful as movement in your data space. Okay, so you're going to kind of be playing around with what do those concepts look like with a data set and a encoder kind of CNN, convolutional neural network architecture there. And then the last part of the homework 3 is going to start to look at the Lie group action stuff that we're not quite finished with until Tuesday, so you can probably just hold off on that until next week. But you can start playing with the autoencoder and thinking about that as soon as you see the homework this afternoon. Okay, so yeah, that's the homework. And yes, reminder, the project proposal is due on Tuesday. And yes, there will be a Canvas place to put that. Anybody have any questions about? Yeah.
When will the homework due?
The homework's gonna, I've set it to be due the Monday before the holiday. I didn't want to make it Tuesday on a holiday. I don't know if that's allowed or not. But yeah, but just 11/6. So you have you'll have 1, 2, yeah, 2 weeks plus 4 days. So 2.5 weeks. Okay, and then there will be, I think, because we're trying to leave some time for you to just focus purely on the project or the project, final project and the presentation you have to do for maybe the last week or so class, not to have any homeworks due. We're thinking to have the final homework come out maybe with a little bit of overlap in case, just because it can't really release on I mean, I guess I could release on the Monday. It doesn't matter. I mean, I can give it to you a little bit early also. But for it to be due just the day before Thanksgiving, before everybody goes on the Thanksgiving break. So it's not due right as you get back from the break. It's kind of awkward. So then you'll have after Thanksgiving to focus purely on the project. I think that gives you like 2.5 weeks for homework 3, 2.5 weeks for homework 4, just to give you the lay of the final workload here. Okay. Yeah.
What's the last lots of content that we need for homework 3.
Yeah, the last content you need is Lie group actions on Tuesday, but that's only for the last couple of problems. I think there's 9 questions, so you can do the first 7 of them right now as we speak. So you can get pretty far into it already without the Lie group. The Lie group stuff is kind of at the very end and more smaller part of it, I would say. Okay, any other questions? All right, great. Stop sharing stuff. Turn this thing off. Hopefully. Okay, let's really quickly remind ourselves where we were. We talked about a group E is a set with a binary operation. Which we would just write as concatenation XY for any 2 elements X and Y and P. And by this I mean XY has to be a valid element in P. We say that's the closure. And it has to satisfy associativity. It has to have an identity element. And it has to be everything has to have an inverse. Every element has an inverse. I won't write out all those things. Actually, maybe I will there quick. The associativity, remember, is that X, Y, Z is the same as X, Y, Z, with the Y and Z happening, multiplication happening first, and so the X, Y happening first. The identity element is this element we usually denote E in the generic case. And it just means that you multiply by E and you get the same thing back. And then inverses means that X for any X and G, there exists an X inverse such that X times X inverse or X inverse times X is the identity. Okay, and you need to be rigorous to say for all X, Y, and Z in G here. And there exists in E, there exists X inverse, but you get the my quick shorthand here. Okay, so that was a group. And then at the very end of the lecture, we introduced Lie groups. That's where we'll pick up. And a Lie group is a group, but it's also a manifold. Such that the group operation, the algebra of the group works nicely with the differentiable structure of the manifold. So Lie group G is a group and a smooth manifold. Such that multiplication, the mapping that takes a pair XY both in G and maps them to XY, the multiplied things, and this is a mapping from G cross G through G. In other words, it takes 2 elements of G, an ordered pair from both in G, and maps it to a single element of G, which is their multiplication. This has to be a smooth mapping. By the way, I'm using the word smooth throughout here. meaning infinitely differentiable. So we talked about different levels of differentiability of manifolds. You can be like this first differentiable, C1, C2 for second differentiable. But I'm going to just declare we're only interested in C infinite smooth. The infinite, so infinite differentiability. I can get as many derivatives as I want. And all the examples of Lie groups we're doing that we saw last time and that we'll do in the class will be C infinite. Things like matrices, those groups are C infinite manifolds. Okay. And then the second thing is the other algebraic thing I can do with an element is invert it. So the mapping that takes X to its inverse, which is the mapping from G back to itself, is a smooth mapping. Okay, and if your algebra satisfies these smoothness properties as mappings, as geometry, then we have a Lie group. Okay. Any questions about just the basic definitions to start with, but just to review? Okay. There we go. Questions? Oh no. Okay. So right, and just to remind us, yeah, question. Go ahead.
Do you mean that the dot product provides you the direct multiplication of XY or what?
No, this is not. So there's no dot product here. We don't have a dot product or a vector space even here necessarily. We only have this binary operation, which again, depending on the group we're talking about, could be different things. And so let's just, yeah, I was going to do maybe come back to some of the examples we had. So let's do some examples of some groups. We did examples of groups, and they all turned out to be also Lie groups. I don't think we didn't get to the point that yes, they're all Lie groups. I can't remember if I said that at the end last time because I kind of got to the definite Lie group and then stopped. But yeah, let's do the some examples. These examples again, they're all Lie group examples to be clear. One would be the group of real numbers greater than 0, positive real numbers, under just scalar multiplication as the group operation. Okay, it's pretty clear that multiplication is a differentiable function, right? If I take the derivative in either the x or y, I get a derivative, I can differentiate that multiplication clearly. And inverse, which is x, remember maps to 1 over x, division is also differentiable. I mean, I don't have that, I can never get x equal to 0, so that's all safe. Okay, so it's pretty clear to see that this group does satisfy those differentiability properties that we need. Okay, so this is our probably our simplest example of a Lie group that's interesting. I should say that maybe I should have done a 0 example, which is just G equals the real numbers, the real line under addition. And I can extend that to b-dimensional vectors as well. And of course, addition, and be careful, the group operation here is I take two numbers or two vectors, and this xy would mean add them. Okay, so our abstract notation for just general groups, we would probably want to change it for that specific example because I would want to say this is x plus y. And of course, addition is differentiable. The inverse is just negation. X maps to negative x is the inverse of x. That's also differentiable very trivially. So vector spaces, real value vector spaces, or real vector spaces, I should say, are Lie groups. They have a group structure under addition. And so Euclidean space basically is a Lie group. It's kind of the simplest example, if you will, of a Lie group. Okay. So does that help maybe answer your question? The XY that I'm writing there is the general group operation for just this I mean, this is for any Lie group, but there's lots of examples, and that group operation may be different depending on the example. And you have to verify that these properties hold depending on which operation and what group you're doing. The more interesting examples we got to, let's see if I don't miss, would be that G equals some type of matrix group. And sort of the parent of all matrix groups, if you will, at least real valued ones, would be the general linear group of dimension D. And sometimes you'll see an R in there, like the real numbers in there, because you could also do this over complex numbers or some other thing. But usually, if I just say GL of D, I mean over real value matrices. So these, remember, are the D by D matrices. D by D matrices. With determinant not equal to 0, so they're non-singular, and that's important because I need to be able to invert them to be a group. And yeah, the group operation here is under matrix multiplication. That's the group operation. Okay. So yeah, we saw that was a group. I just hand waved and said that's a group because you can invert matrix multiplication is associative, and the identity matrix is your identity element. It's maybe a little bit trickier to see that matrix multiplication. I mean, probably not if you've done some linear algebra, more advanced linear algebra. That matrix multiplication is differentiable. In the end, if you wrote out whatever dimension, right, you wrote out matrix multiplication, right, it would just only be like quadratic in, things here. Or if you're doing just one of matrix values at a time, it's actually linear in one thing at a time. So yeah, so this is differentiable. Matrix multiplication is differentiable. The trickier thing is inversion, right? That inversion is a polynomial in the matrix elements. The elements of the inverse matrix are always just polynomial functions of the input elements of matrix, and that also is differentiable because it's polynomial. Okay, so yeah, so the bottom line is that GL of D is also a Lie group. I guess we didn't. Maybe we did, I can't remember if we did, argue. I guess one thing I need to actually argue before because I was going to say it's differentiable, that's actually, I skipped a step, because I need to also be able to argue, we can see it's an algebraically a group, but I didn't necessarily argue it's a smooth manifold. So it turns out that if you look at determinant not equal to 0 as the specification for this set GL of D, the argument, and again, being very hand wavy and not a rigorous proof of anything, because we want to get on to lots of other stuff. The determinant not equal to 0, that specifies all matrices that specify this are an open subset of the space of all D by D matrices. And if you think about all D by D matrices, that's just a D squared dimensional vector space, right? It's just Euclidean space of dimension D squared. And so an open set of RD squared is a manifold, right? Because it's just an open set, open set of Euclidean space is locally Euclidean. So, so this is how you can see that GL of D is a smooth manifold. It's just an open set of a Euclidean space. Okay, right. And then the only other example I'll worry about for the purposes of today's lecture is the special orthogonal group of dimension, again, D by D matrices that are rotation matrices now. And as we said, this is a subset of GL of D, because any rotation matrix has determinant 1, so it also satisfies the non-singularity, of course. It's actually a subgroup. Obviously, you're using the same group operation, matrix multiplication here. So then everything we've argued about GL of D, that it's differentiable operations, it will carry over to SOD. The thing you do have to verify is that that SOD is a smooth manifold. There's other than the determinant of R equals 1, this is the two conditions you need for, I should put them in the opposite order technically, frankly, because R is in SOD, so if this is true, then this is, whoops. Then this means that R is a rotation matrix. Oops. Bring it there. Yeah, so SOD. And this is saying that rotation matrices, the really key ingredient is that their inverse is their transpose. So R times the transpose gives you identity back. Now, this means that this already, if I take the determinant of both sides, tells me that R has either determinant 1 or -1. And so this is just picking, this extra constraint just picks the connected component, which is the +1 component. There is like two disconnected manifolds, the +1 and the -1 are two manifolds that don't intersect, obviously. And so this is the key constraint. And what you can show is that this was, I think, in one of the Long's lectures back a while ago when we were talking about manifolds. We talked about again, hand wavy in the slides there. It was kind of part of the quotient spaces and shape stuff, and we had these things that are manifolds. SOD was one of them, and this constraint, again, it's just polynomial in the entries of R. And so if you use the inverse function theorem, the implicit function theorem, you can show that if you remember this from multivariate calculus, the implicit function theorem basically will say that anything that looks like a smooth constraint can be seen as a manifold. So it just shows that that SOD is a manifold. Again, just hand waving over that argument. So that plus the inheritance of the GLD being smooth multiplication, smooth inverse, because it's still matrices. Again, hand waving, SOD is also weaker. Okay, and these are the key things when we're doing transformations of shapes, transformations of images, and other things like we talked about control theory, controlling like self-driving cars or drones or robots, and things like protein molecules folding and things like this. So these are kind of the key transformation groups. This just scaling multiplication gives you scaling. RD back here can give you translation, for example, if you're in d-dimensional space, you want to translate an object or an image or something like that. GLD can give you things like affine transformations, scaling and shearing, and stretching in particular dimensions, and in addition to rotations, obviously. So all of these transformation groups, you can think of these as transformation groups, they tend to be used as transformations of things like geometry or images or what have you. Okay, and they're the key ones we're going to be talking about today and Tuesday. Any questions on those examples? Okay, so the next thing, sorry for the Zoomers as I went to get the eraser, it's going to flip a couple boards here, hopefully follow me, there we go. The next thing I want to talk about is something called a homomorphism. So again, you see a word that has morphism at the end of it, like homeomorphism, remember, was topology, was an equivalence, a continuous transformation that's invertible, and so it's bijective, invertible, and the inverse is also continuous. So you have topological spaces that are equivalent if there's a homeomorphism, where I emphasize the E there because it's different from what we're talking about now as a homomorphism. And we had diffeomorphisms between manifolds, it's bijective and smooth in both directions. And we had isomorphisms when you have a metric, an isomorphism isometry, an isometry there's a morphisms not in the word. But isometry would give you this metric carrying over between metric spaces and Riemannian manifolds in that case. So yeah, so now in algebra, we have a concept of homomorphism. And this is not an equivalence, it's a one-way thing. So it's maybe more like a continuous, it's the analogy in topology to continuous transformation. It's the one-way transformation that will preserve the algebraic operation. So a homomorphism between two groups is a mapping, I should say, it's a mapping between two groups. I'll write it as phi between G1 to G2. So G1 and G2 are groups. And it has to satisfy the following. It has to be the case that, oops, wrong letter. Phi of G inverse. But let me actually do following phi of G times H is equal to phi of G times phi of H. And this is for all G and H elements in the input group. And it has to be the case that inverses are preserved. With phi of G inverses is equal to the inverse of phi of G in the output group. So phi of G is in 2. So this is the inverse on the G1 group. That inverse can come outside the phi and be applied after you apply phi on the G2 group. And again, this has to be the case for all G in G1. Okay. So let's see what this is saying. I kind of have said it already, but just if I'm doing multiplication on the G1 group, G times H, I get a value out that is again a point. G times H is a point in G1, and then I map that output of that multiplication over to G2. I would get the same thing as if I took the two G and H points individually, mapped them over to G2, and did the multiplication over G2. Okay, and then I think I've already kind of said it here. I can do the inverse over here and map it over, or I can map it over to G2 and then apply the inverse in G2. Another way of thinking of this is multiplication and the phi mapping commute with each other. Inverse and the phi mapping commute with each other. I can do the one first or second. Okay. If you put these two rules together, one property, so these are the rules, these are the only two rules. One property that immediately comes out, you don't need to specify it as a rule because it comes out, you just set H to G inverse here. What you can see that the identity element, which I'll write as E1, that's the identity element in G1, is equal to the identity element in G2. Okay, so it takes the identity element of the input group and maps it to the identity element of the output group. Okay. Any questions about this concept of homomorphism? So the equivalence between two groups, if G1 and G2 were basically equivalent as groups, so I can say that would need them to be a bijective. This would be a bijective map between the two groups as sets, and then I'd want it to be a homomorphism in the forward direction and a homomorphism in the inverse direction. In that case, we call it isomorphism. So and we won't really talk about isomorphisms anymore. Homomorphisms is the one we really are going to care about. It's more interesting for us when we do Lie groups here. But just to complete that circle, to relate it to homeomorphisms, diffeomorphisms, all the morphisms we've talked about that were really equivalences, it was kind of goes in both directions and bijection there. Okay, so yeah, bottom line is that homomorphism is something that will map you to one group to another, and all the algebra you were in terms of the group you were doing over here will get nicely mapped out over here. Okay. As you can imagine, if we were dealing with a Lie group, I can just add a Lie group homomorphism. Now let's say G1 and G2 are Lie groups. I would need phi to be a smooth mapping. I would need to add that extra condition. Okay, so if I just care about groups in algebra, then I don't care about smoothness, differentiability, but if I'm doing Lie groups, I'd like my homomorphisms in general to be the group homomorphism, but also make sure it's smooth mapping so that these manifolds are differentially mapped to each other, one to the other. Okay. Okay, and so with that kind of setup, I want to give a quick example of a homomorphism, a very simple one. A Lie group, I should say a Lie group homomorphism, and coming back to our examples here. Okay, yeah, the camera, no, the camera, shoot, the camera's in the wrong. But hopefully people on Zoom saw some of that, what I wrote on the board over there. Not sure when it got lost.
That's all right. It was just the last few seconds.
So a really quick example that everyone's familiar with, but you didn't realize you were doing Lie group homomorphisms probably, is the following. Let's take G1 equal to the real line. And I'm going to write it in the following way to make it clear what I'm doing here. That what the operation is. This is real line under addition. So it's like 0 example if there with D equals 1. Okay. And let's take G2 equal to the positive reals under multiplication. So that X means multiplication, just scalar, usual numbers, multiplying real numbers. Okay. So these are my two groups. What's my phi? You might guess what the phi is going to be. That might take me from addition to multiplication. What do you know a function that will take me from additive to multiplicative? Just think of all the functions you know. These are log. Yeah, you're yes. Yeah, I was gonna say you're going from T2 to T1, you're right. If I was going the other way, but yeah, the opposite way, it would be exponential. So so now I'm gonna say phi here is just the exponential function. And nothing, we've used the word exponential in terms of Riemannian manifolds, but this is just our usual exponential function. So we can check these properties. So property 1, I'm just going to start writing exponential instead of phi. You have to remember that the inputs to phi are additive. So I'm going to write this as G plus H. G and H are in group 1, which is addition, real numbers under addition. And the question is, does that equal exponential of G? And now this is going to be this concatenation over here, if it were to come with me. This concatenation is now multiplication. So I'll keep writing it as, well, no, actually I'll use the X because I put the X here. So let me say, is this equal to exponential G times exponential H? And the answer is yes. We all know this rule from our, intro calculus course probably, or maybe even earlier, that addition inside the exponent can be pulled out to multiplication outside of the field. Okay. And then rule number 2, I think everybody can see where we're going here. Exponential, again, what is inverse under addition? It's just negation. So exponential of minus G, that's the G inverse on the G1 group, is equal to exponential G inverse. And again, this checks out. We know that negating the exponent in an exponential is the same thing as 1 over, I can just rewrite this as 1 over exponent G. What I just include what I mean by inverse, sorry, camera. Inverse here, multiplicative inverse just means divide 1/. Okay, so rules check out. We of course know that exponential as a function is a infinitely differentiable function, so it's also a smooth mapping between G1 and G2 if we think of those as manifolds. Okay, now these very sort of almost trivial manifolds that are just one-dimensional lines. One just happens to end at 0, open interval, but the other one's the whole real line, but they're just one-dimensional manifolds. But we see that we have a different algebraic structure between the two, but they are mappable one to the other through the exponential function. And yeah, as you were saying there, this happens to be an invertible homomorphism. I can go the opposite way with log, right? And everything checks out the other way with log. So I really have a homomorphism bijection G1 to G2, G2 back to G1. I've got a, which by the way is a diffeomorphism of manifolds, and it's a isomorphism of groups. So it's an isomorphism of Lie groups here. Okay, so very simple, basic example that everyone's familiar with as our first example of a Lie group homomorphism. Any questions about that example? Okay. So what we want to do now is, okay, what we want to do now is kind of build on that particular example of homomorphism to define the next very important concept in Lie groups, which is this concept of one parameter subgroups. So one parameter subgroup is a subgroup generated by a homomorphism from the real line under addition, that G1 group we have over there, to your Lie group G. Okay, so we're given a Lie group G, the Lie group G and a homomorphism. Again, this is a Lie group homomorphism. So it's smooth in addition to being a group homomorphism between R, and I'm going to again specify that to be very clear. I'm talking about the real numbers under addition to your group, your Lie group G. Okay, and the set of all outputs of phi are a subgroup of G. That's the one parameter subgroup, and we'll get into this a little bit more here. So let's kind of break down what's going on here. So if I have a homomorphism from the real line to my group G, the one thing I know already, actually let's draw a picture. This is usually helpful for me at least. I'm going to draw pictures of manifolds again because your Lie groups are manifolds. And there's a very special point on our manifold, the identity element. It's kind of unique because it plays an important role in the algebra. We'll see it actually plays a very important role in the geometry as well. But the first thing we are going to notice about this phi function, this homomorphism, is if I ignore the homomorphism part, and I just think of it as a mapping of manifolds, it has to be a smooth mapping from a real line to G. So I have, I could call this value T. I've got this phi of T. I mean, as a manifold mapping, this is just what we call a smooth curve, right? So I just have a T parameter that goes from -infinity to infinity, and its output is in G, and it's a smooth function. So that has to be a smooth curve, phi of T. Okay, and that curve forms a subgroup. So it is a group all by itself, sitting inside your manifold that is one-dimensional smooth curve, but it's also a group because it has this homomorphism from the real line. Okay, what we also know from the fact that now that we do use the fact it's a homomorphism, we know that phi of 0 is the identity element. So at t equals 0, I know exactly where I'll be. I'll be at E, the identity element of my Lie group. All right. And yeah, like I said, we know that the homomorphism property is that phi of s plus t is equal to phi of s times phi of t on the group. And so what that says is if you give me 2 points, phi of s, phi of t on the group, and I multiply them together under whatever my Lie group operation is, I'm going to get an output of 3rd point. So let me make this phi of s. This is phi of t. I'm going to get a 3rd point, which is phi of s plus t. And so another way of saying that is if I move to time s, I move to time t. If I multiply these two things together, I'll still be on the same curve that this homomorphism gave me, but it'll just be s plus t is the time I need to move towards to get to that point. Now notice this goes from plus infinity to minus infinity to plus infinity. So I've kind of drawn this like it ends, but it really just keeps on going forever. Now it may be that it's cyclical, it moves back around on itself. That's also possible, but the point is it doesn't just stop. It's not like a segment that just stops. It may asymptotically slow down or something crazy like that, but it's not going to end at a point. It's really just it's going to kind of go all time. Okay, so these are some of the things going on here. Another thing to point out is that if I'm at a point phi of t, let's say, I also know that if I went the opposite direction to phi of minus t along this curve, that again, because of the rules of a homomorphism, rule number 2, this is the same thing as the inverse under my group G. So phi of t has an inverse also in this one parameter subgroup over here, just going minus t in the opposite direction from the identity. If the identity starts at 0, I go minus t instead of positive t. Those are going to be inverses of each other. And so you see that because of this rule, this curve is closed under multiplication in the big group G. It's closed under inverse, so it's a group itself. It's a subgroup. Sorry, camera again. Okay. So any questions about one parameter subgroups? The idea is that if you have a Lie group, and you can define a homomorphism from real numbers under addition, and basic Lie group, if you will, to your Lie group, then you have a one-dimensional smooth curve, which is a group in and of itself. Now, what we haven't said is, do these things even exist? Can you do this? Like, if I give you any Lie group I want, like let's say GLD, the general linear group of matrices, is it possible to find such homomorphisms and these curves that are kind of like one-dimensional groups inside of my big group? The answer is yes, these always exist, and we can characterize exactly what they are for any Lie group. And that's the next thing I'll talk about. And I'll try to give it a little bit of motivation, maybe. Let me see. Yeah, let me hold off on the motivation. The motivation, well, I'll give you the really quick gloss over motivation for a minute here. We'll come back to it on Tuesday when we talk about group actions. But when we talk about group actions, and you'll see a little bit in the homework as well, when we talk about one parameter subgroups, you can think of a group acting on an object on some set. So if again, we're thinking transformation groups, think of like rotating images or translating shapes or something like this. is a group action. We'll get into more details next week. But one thing where one parameter subgroups come out is in differential equations that bodies of motion, for instance, satisfy. If I give you initial conditions, and I give you an ordinary differential equation for like equations of motion under some kind of initial kind of force, it turns out that differential equations very often that look like that are one parameter subgroups on the group that is acting on the bodies of motion, like rotation and translation, things like this. So one parameter subgroups are very important in differential equations, solving ordinary differential equations. When you can write your differential equations under some group action. So that's one example of it. What we're going to use them for in a minute is here is just to see how we can get tangent spaces for our Lie groups and the algebraic structure that you can put on the tangent space of a Lie group. Okay, so I'll redraw this picture. I've got a group, Lie group G. I've got the identity element. And again, because my Lie group is manifold, I've got tangent spaces at any point on my manifold. I'm going to be particularly interested in the tangent space of my manifold at the particular point, the identity. Okay, and remember our notation for tangent space is T, what point are you, and then the manifold. So TEG is the tangent space at the identity element of G. Okay, and again, just to review, if G is a D-dimensional manifold, we know this is a D-dimensional, this TEG is a D-dimensional vector space, right? And the things here are the tangent in this space are the tangent vectors that are anchored at the identity element. Okay.
Hey, we lost you on the video.
You'll see in the notes that there is this font, which I can't draw easily on the board, but I'll kind of try to emulate it. It's very kind of like old, looks like maybe like Dracula would use this font, like an old German font called Fraktur. And so that's there's a lowercase g in this Fraktur font. It's old German font, Fraktur font. That is the classic notation for the tangent space identity of a Lie group is you just lowercase the Lie group letter and you make it this weird Fraktur font. I mean, whoever came up with this notation didn't have to do this on a blackboard, I think. So anyway, it takes like 30 seconds for me to write this G. So I'm not going to write it that way. I'm going to, on the blackboard, you'll see me write. I think I'm just going to do like a G, which has a funny loop on it. Just that's my Lie group. My tangent space to the Lie group at the identity. Okay. And so why do we care about the tangent space at identity? Coming back to the one parameter subgroups, what we want to know is that, let me just erase all my other tangent vectors, just have one of these tangent vectors in TEG. If you give me a tangent vector, remember tangent vectors are velocities of curves. And so the question is there a one parameter subgroup that has this velocity? And the answer is yes, there's always a one parameter subgroup, a uniquely defined one parameter subgroup for any velocity you give me in G here. So usually again, Lie groups, we would write the tangent vectors at identity with capital letters. So I use capital X. We were using like lowercase like these, U's and B's for tangent vectors, but Lie groups, we'll see in a minute, the tangent space has this interesting structure, and we're going to use a capital letter X. So let me say if I have X in, again, that's the tangent space at identity. What I want is, again, a homomorphism. Because Lie group homomorphism or one parameter subgroup homomorphism B from the real line under addition to my Lie algebra. And the condition I want is, I've already got the condition that at phi of 0, I'm at the identity. I just want to specify what the velocity now, the first derivative of phi is at the identity. So I'm going to say d phi dt at t equals 0 should equal this vector x that I've specified. Okay. And this is where the differential equations come in, by the way, because this is just an ordinary, oh, actually, sorry. I haven't actually specified the differential equation. I've given the initial condition, but I haven't told you what the differential equation is yet. Right. So yeah, so it turns out that yes, you can do this. And what we need to do is now I need to specify to you what is the differential equation that such a one parameter subgroup would satisfy. And to do that, we need something called left multiplication by G, and thinking of that as a mapping from the Lie group back to itself. What does that mean? You can probably already kind of see what it means. It means LG of another element H is an element, and G is just multiply on the left by G. Okay, so this is a mapping. Left multiplication by G is a mapping. Give me an input H, I give you an output G times H. And now, because this is a Lie group, we know multiplication is a smooth mapping. So this is a smooth mapping of manifolds of G back to itself. It turns out it's actually a diffeomorphism of G back to itself, diffeomorphically. Okay, and what we're going to do is we're going to then say, okay, I've got this smooth mapping. And if I have a smooth mapping of G back to G, then I know that, let's take an example. If I take the identity element, LG of the identity is G times E, which is just G. So it's going to map the identity E to the point G. But it's also, if I take the derivative of this mapping, it takes the tangent space at E to the tangent space at G. Okay, and what I mean by that is if I give you any tangent vector at E, it will get mapped by the derivative to a tangent vector at G. Remember, that's what we do. We can do with smooth mappings. And so the derivative of LG, I think in the notes I write this as LG star, but we could also write it as DLG. Will map my tangent vector X to a tangent vector in the tangent space now at G instead of E. Okay, so this X maps to another tangent vector here at G. And while I'm going through all of this, the point is that what I want to do is I want a differential equation that you always follow, no matter where you are in G. Your curve should always follow the same vector, just with this left multiplication. This is called a left invariant vector field. If I take all possible G's and take this X, I keep X fixed at identity, and all possible G's, I multiply. So this would be like, say, G1, G2, whatever, everywhere in my manifold. I will specify a vector there, which is just the multiplication, left multiplication derivative from E to that new base point. Let me write that out more. Stupid camera. Sorry again to the Zoomers. Let me repeat that because I think that might have been lost. I'll write it down mathematically in just a minute, but just intuitively what we're doing is left multiplication takes me from one point to G times that point. So from E to G, for example, and the derivative of that mapping takes this tangent space to any other tangent space. I can go from identity to any other tangent space just by left multiplication derivative to a new base point is the idea, and it'll move that tangent space there. And so if I specify just one vector at the identity, I can just kind of spread that vector all around to any other point through this left multiplication derivative. By the way, there's nothing special about left. Okay, the camera just did it to me again. That time I caught it. I get too far over here, it loses me. Thanks, that's weird. I'm not off the camera. Anyway, there's nothing special about left. You can also do right multiplication and just repeat this whole process we're doing with right multiplication. So pick one, left or right, whichever you prefer, and run with that. Okay, so that gives me a vector field called a left invariant vector field. I'll write that down sort of explicitly. Left invariant vector field on G. Well, there's the pictures over there. I won't redraw it. I'm going to write this now as X of G. And so that means give me a point for every point on the manifold capital G. I'll return a vector in that tangent space. This is always me a vector in the tangent space at the base point little g. Okay, and its value is always going to be just the derivative of the left multiplication operation, smooth mapping, by g applied to X at the identity, which is the original thing I started out with. So you have to give it this one value at the identity. You give it a vector, and then all the rest of the manifold. There's a vector field, a smooth vector field in the manifold, X of G. Okay, and now the one parameter subgroups that we wanted here, the phi, is just going to satisfy the following differential equation, d phi dt at any t. So we had it specified. I was specifying it, if I wanted to specify it at time 0 to have this velocity, the following differential equation. This is left multiplication by dt of X identity. Okay. So this is a little bit, we have to parse this carefully. So now we'll draw the picture again. At the identity, I've specified X, or I could call it X of 0, the velocity of my one parameter subgroup at the identity. And I've got a curve. I want to say I want a one parameter subgroup that goes through there. If I satisfy this differential equation, which means that as you move along to some time t, you take X of 0, multiply it. That gives you your X of phi of t. That's, or I should say the d phi dt. So that gives me my velocity going forward. Or back. I just have to integrate. If you give me a left invariant vector field, this is really to find everyone in the manifold. But if I just integrate that vector field, I just stay following that direction. I get the one parameter subgroup. I'll satisfy these conditions that give me a one parameter subgroup. Okay, so the bottom line here is that the one parameter subgroups of a Lie group come directly from just the vectors, tangent vectors at the identity. So if you give me a tangent vector at the identity, I get a unique one parameter subgroup. Okay, and that's the only way to get a one parameter subgroup. There are no other one parameter subgroups. Okay, but notice what this means is because I've got this whole tangent space to play with, this d-dimensional tangent space to play with. The camera keeps losing me, I don't understand. Okay. Then I can really go off in any possible direction you want, and at any kind of speed, I can stretch this or slow it down. But I can really get curves in all directions from the identity that are subgroups, one-dimensional smooth curves that are subgroups of my Lie group. Okay. But also, what this is telling me that this tangent space is sort of in this one-to-one relationship with the one-parameter subgroups. Every tangent vector has a one-parameter subgroup, and any one-parameter subgroup has a tangent vector. The initial velocity determines it exactly. So this tangent space is, you can think it's also the space of all one-parameter subgroups. Okay, I'm almost out of time. A little bit behind where I thought I'd be, because today's topic was about Lie algebras, and with 2 minutes to go, I have not mentioned what is a Lie algebra yet. So I'll have to leave it as a little bit of a cliffhanger, but I can introduce it. What we've done basically now is define a Lie algebra for a Lie group. So the Lie algebra of a Lie group is this tangent space at identity, this fractor G tangent space. This is something called a Lie algebra. And the first thing we've noticed about this tangent space at identity is it's a very special tangent space because all one-parameter subgroups emanate from that tangent space velocities. And so that's the first thing to notice. But what makes it a Lie algebra? It's not just a vector space. We know it's a vector space because manifolds always have vector spaces as their tangent spaces, but it has more to it than just vector space properties. It has an algebra property, more algebraic structure, which I don't think I have time to do. But it's in the notes, and I'll start with it on Tuesday. What we'll see is that if I give you two tangent vectors, x and y, in my tangent space identity, or Lie algebra, then not only can I add these because they're vectors, I can scale them because they're vectors, I can also multiply them with each other. This is not something I can usually do with vectors. And this is the multiplication of x with y is written this way with the square brackets. This is called the Lie bracket. And again, calling it multiplication, you can think of it as a multiplication, but in the sense that it's another binary operation that puts x and y together. It's different from addition. And we don't have time to explain exactly what that is, but this extra structure falls out of just the fact that it is a tangent space at the identity to a Lie group. It will have this extra algebraic structure just naturally fall out, and through the one-parameter subgroups that we just introduced, that we'll see that now I can actually also talk about multiplication of tangent vectors, which I couldn't do before. There was never a multiplication of tangent vectors. It's a special property of this particular tangent space for Lie groups. Okay, and I'm out of time. I won't motivate any further than that. So I'll see everybody on Tuesday. The audio was disabled. Sorry about that. Yeah.